So let's look at a couple of problems that you will see, at least one example of problems that you will see on an upcoming quiz or a test that you are going to be taking for the carbohydrate module. And this is one of them. This is a very straightforward example, and honestly you're not going to see anything more complicated than this. So once again, I've told you that you don't need to memorize the structures of any disaccharide. What we want to do is that we want to take a look at the structures of the disaccharides and kind of pick apart the pieces that make it up. That's actually more important than memorizing these horrible structures that you are seeing on your screen at this moment. So this is a disaccharide. That's two sugars that are hooked up together by a glycosidic bond. Now, where is the glycosidic bond? Well, I've kind of left out something here on purpose because I want you to take a close attention to it. There's an oxygen right here. So wherever that oxygen is that connects the two sugars together, that is the glycosidic bond. So glycosidic bond or glycosidic linkage, that terminology's up to you. Whatever you want to basically use, you're more than welcome to do so. So this is glycosidic linkage. Now, the questions that we will see from these disaccharides will be, number one, what monosaccharides make the disaccharide up? So, AKA, that means label in this diagram the monosaccharide on the top, and label in this diagram the monosaccharide on the bottom. And then what type of glycosidic linkage do we have? Do we have an alpha and a beta? Do we have a 1,4? Or do we have something different? So these are the questions that we are after. And this is the information that we should really understand and take away from the disaccharide portion of the lecture. So let's take a look at this problem, and let's look at the monosaccharides that make this thing up. So how do I determine what type of monosaccharides do I have? Well, you kind of do it in steps at a time. So we know that this is divided up into two pieces. So I'm just going to kind of draw a dashed line here, and we're going to start with the top one first. So we know that this is a monosaccharide, right? Monosaccharide. And we need to figure out what type of monosaccharide. So I take a look at the number of carbons. So I see 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon, and 6 carbons in total. Okay, so 1, 2, 3, 4, 5, and 6. On the first carbon, this is where the glycosidic linkage is happening, and this first carbon is also where the oxygen of the ring is attached. So that basically means that this carbon was the carbon that had the carbonyl on it, because that's the one that's attached to the oxygen in the ring. So that means on my number 1 carbon, that's my C double bond OH. At least it was before it made the ring. This one, well, we always just assume that we're working with D sugars, and that's what I'm going to tell you as well, because that's what this whole lecture was about, and your body works on D sugars, so there's no really reason for us to use L sugars in these examples. So this carbon did have an OH on it, and there was the oxygen. It's just now incorporated in the ring. So the question you might have is, how do I know which side it goes on? Well, we always assume that we work with D sugars unless we're told something different. So it's got to go to the right hand side. And then finally, the last carbon is basically a CH2OH. So I'm just going to write CH2OH here. Okay, so we need now to find the structure of the sugar that's a 6-carbon chain that has OH on the right, left, right, right. And hopefully you can quickly pick that out and know that that is glucose. So the number 1 sugar, the one up at the top, that is a glucose. And glucose is bonded to another monosaccharide in this picture. And that monosaccharide we're going to have to define as well. We're going to have to figure out which one do we have. So again, I do the same thing. I look at the total number of carbons, right? So here is the hookup, and that's also the carbon that's attached to the oxygen. So number 1 and 2 and 3 and 4 and 5 and 6. So there's 6 carbons here as well, right? So 1, 2, 3, 4, 5, and 6. Okay, well the problem here is that at this spot, that is not the number 1 carbon in the chain, right? If this is the carbon chain that we have basically circled with the green dots, well that's not the number 1 carbon. This is actually the first carbon in the chain, the CH2OH. And then it gets on the anomeric carbon, which is then attached to the oxygen of the ring. And this lets me know that the second carbon in the chain actually has the double bond O on it, unlike this one up above, right? This one from up above, in the ring itself, this first carbon that was attached to the oxygen, it didn't have anything else attached to it, no other carbons at all. So that meant it was the first carbon of the chain, and the first carbon gets the carbonyl. In this example, however, this is the anomeric carbon, and this anomeric carbon does have a CH2OH on it. So it's not the first carbon of the chain here. The anomeric carbon is the second carbon of the chain. So we get this CH2OH that points up here at the top, and then we get to the anomeric carbon that's bonded to the oxygen of the ring. So that's the one that has the double bond O on it, or what did have the double bond O on it. And then everything else happens just like from up above. The OH group points up, so that means here it goes left-handed. The OH group points down, so that means here it goes right-handed. Then we get to this carbon. This carbon did have an OH on it, but that O is now involved in the ring. So we've said before, if it has an OH and we know the OH is there, we assume that these are D sugars that we're working with unless we're told something different. So the OH goes right-handed again. And then finally the last carbon is my CH2OH structure. Okay, so the differences here is that this was an aldose up here at the top. It came from an aldehyde, right? So here's my aldehyde group. And this one came from a ketose, because here's the C double bond O in the chain, and I need to find the ketose that actually matches up with that structure. So I need to go to the chart. I need to probably look at the ketoses, look at ones that have 6 carbons on it, and then I need to look for ones that have the OH that points left, then right, then right. And when you do that, you're going to see that this is fructose. So this disaccharide is made up of a mono unit of glucose and a mono unit of fructose. So glucose and fructose are coming together for me to make this disaccharide. Okay, so the first part of the question is answered. Okay, those are the 2 sugars that make it up. Now I need to figure out what type of bond do I have? What type of glycosidic linkage am I really working with? Now, if you're not careful, this could be a little tricky. So we're going to have to work through this question as well. The problem here is that glucose has its linkage at carbon number 1. Okay, so we know that maybe a 1 is going to be involved, just like before. Now that is connected to the fructose that's down below. And this fructose that's down below, the issue here is that that's connected to the anomeric carbon. Now, in the other monosaccharide that we saw, it was connected to like carbon number 4, or you might see disaccharides that are connected to a different carbon over here on the left-hand side. But for this example, this is connected to the anomeric carbon on fructose, and that's number 2 in the chain, right? So we really have a 1 and a 2 linkage that's involved. The problem, though, is that both of these are anomeric. So I'm going to have to be very specific on which one I'm going to call it. So that means that a alpha or beta has to go with the glucose, and an alpha or a beta has to go with the fructose. And that's very important because both of those are on the anomeric carbon, and both of these need that alpha or beta to describe how they are linked. So with the glucose, this bond is pointed down. That's one of the reasons that we draw it the way that we do. So this is actually an alpha. Now, if I look at the fructose, well, the OH group was pointed up here. And that, of course, OH group was converted over to this oxygen bond that connected the two sugars together. So this OH points up, or it pointed up. So that is the definition of a beta sugar. So how do I kind of represent this in an actual name? Well, what we do is that we tell you basically that the bond does happen between the 1 and 2 sugar. So it's not uncommon to see something that looks like this in the nomenclature. So it's a 1,2. However, this is an alpha glucose and a beta fructose that paired up. So we know and understand that the first number listed in the parentheses goes to the first sugar listed in the name, and that is glucose here. And the second number in parentheses goes to the second sugar listed in the name, and that is fructose here. Now, is this the proper name for sucrose, alpha glucose, 1,2 beta fructose? And the answer is no. What they do is that they will go through and they will say alpha D glucopyranosyl because it is a pyranose ring, right? It's a 6-membered ring. Parentheses 1, 2, close the parentheses up, and then beta D fructofuranoside. So that's the proper name that it will go by, but if you had to describe the glycosidic linkage, then this is okay with us. We know that it's a 1,2 linkage, and we know that a alpha is in front and a beta is behind. To kind of save you some trouble here, you could also on the test do alpha parentheses 1, 2, and then beta, and that will let us know that you know what this glycosidic linkage is doing. So, glucose is involved, fructose is involved. That's answer to part 1. Part 2's answer will be the glycosidic linkage is a 1,2 linkage, and the first sugar is alpha, the second sugar is beta, and that's how we can describe it. Now, if I take a look at sucrose, notice there's no really free OH groups at the anomeric carbon. So the question is this sugar, a reducing sugar? And the answer is no, right? At that anomeric carbon, I don't really see a free OH group on the glucose or that free OH group on the fructose as far as directly attached to the anomeric carbon. By the way, this sugar is sucrose. This is your table sugar at home that you love to cook with, and you love to put in your drinks, and you love to eat the cakes and everything else that comes along with natural sweetness. Well, you can thank sucrose for that, and this is the structure for sucrose, one of the most common disaccharides that are out there. So in the next video, we'll take a look maybe at another disaccharide and continue on with the discussion.